Hello dear students, welcome to the series of sessions where I'm talking of few subtopics which are very important for JEE Advanced and also for JEE Mains. In today's session, I will be talking about trigonometric identities using complex number. I will tell you how with the help of complex number like de Moivre theorem, nth root of unity, and also with the help of binomial theorem you can create certain identities of trigonometry which are not that easy otherwise. So let me start this session, but before that I will talk about Daksh, who got All India rank 15 in JEE Advanced 2025. He also got full 120 out of 120 marks in maths JEE Advanced 2025, which is a very rare feat achieved by any student across country. In fact, not every year students are getting that kind of marks. He was student of Aram 22-25, where I was teaching him maths for 3 years. The ideas which I am bringing in these sessions are actually something that we used to discuss in his batch. Few of the ideas came from him also. The motivation of these sessions is, or are, you can say, to get that kind of performance repeated by all of you in this year. Dear students, I am still occupied with my students of Arambh and Eklavya, who will be writing JEE Advanced this year in 2026, and we are very hopeful to repeat this performance this year also. I will like to talk about Eklavya 2026. This is actually the QR code. It is a QR code so that you can join the Telegram channel of Eklavya, where you will get all sort of information about this batch. When will be the batch starting, how you can join it, when will be the entry test, etc. So just join it and you will get all the relevant information in that channel. Okay, so dear students, this is me, Surendra Jain. I am teaching maths for last 14 years. I've been teaching students for mains, advanced, Olympiad, CMI, ISI. So now coming to the topic, that is trigonometric identities using complex numbers. So here I will be first talking about how sin NA, cos NA, tan NA for any general value of n, like 2, 3 you already know, but for 4, 5, 6, 7 if you need, how you can derive it. I will not claim that they are very much used in every year questions, but this is some idea that if you know, you will be having alternate ways to crack some question. Okay, so how sin NA, cos NA, tan NA can be derived, please see. To derive cos NA and sin NA, I will be writing it like this: cos NA plus iota sin NA, which is actually e power iota NA. And I can also write it as e power iota a whole power n, which means it will be cos a plus iota sin a whole raised to the power n. Now you can open it using binomial theorem. So this will become nc0 cos raised to the power na plus nc1 cos raised to the power n minus 1a into iota sin a. Then another term would be nc2 cos raised to the power n minus 2a into iota sin a whole square and so on. Okay, now you just need to compare the real part and imaginary part on both sides. You will get cos NA and sin NA. So what will be cos NA here? It will be first term nc0, then cos raised to the power na, then there will be minus sign because iota square will give you minus 1, and that will be counted in real part. nc2 cos raised to the power n minus 2a sine square and so on. So that will be the formula for cos na. Now sin na will be just you compare the imaginary part. So it will be nc1 cos raised to the power n minus 1a into sin a, that is coming from this term. Okay, then leaving this term, next term would be the iota cube term, so there will be minus sign, and it will be nc3 cos raised to the power n minus 3a sin cube a, and that's it. Not that's it actually, there will be other terms also, but yeah, you have to write all the terms to get this sin NA completely. Now if we are looking for tan NA, Okay, if you're looking for tan NA, I think tan NA can be always written as sin NA upon cos NA. Okay, now I will be using this sin NA and cos NA. This will go in the numerator and this will be going into the denominator. Now to write them easily, what I will do, I will divide both numerator and denominator by cos raised to the power NA. So if this is divided by cos raised to the power NA, here we will be getting tan A, here we will be getting tan cube A, here we will be getting just 1, here tan square A, and so on. So this is how this tan NA formula can be derived easily. You might have seen this formula in many books also, but this is how it comes. So it will be NC1 into tan A, okay, then minus NC3 into tan cube A, and so on. In this case it will be NC0, only NC0, yeah, NC0 minus NC2 tan square A plus, and so on. So this is how your tan NA formula works, or how this is how it comes actually, and this can be useful in many questions. I will show you in today's class itself how tan NA, tan 9A can be used, although you may have some other methods also to solve those questions. But if you know this kind of things easily, this kind of ideas are also, you can say, affordable for you. You can use them, you can apply them in your questions in that paper or whatever thing you are solving. Okay, now one more thing before I go to the question. It is sin A1 plus A2 plus A3 up to AN, then cos, and then tan. Similar way it can be done. Now if I am looking for cos of this A1 plus A2 and so on, plus iota sine of A1 plus A2 and so on. Okay, this will actually be equal to, you can write it as in Euler form, e power iota A1 plus A2 and so on. Okay, you may use de Moivre theorem also, which tells you directly that you write this as cos of A1 plus iota sine A1. This is actually e power iota A1, then into cos of A2 plus iota sine of A2 and so on. Now if you have to write it in general for any n, it may be difficult to write because you may not write it explicitly. I will say not difficult, but writing it explicitly will be difficult. Try to understand the pattern. For real part, that is cos of A1 plus A2 plus A3, you will need all the real part here. So what is the real part? When all the cos are multiplied, that will definitely be coming with real part. And then if you multiply two sines, then iota into iota will become -1, and all remaining cos are multiplied, then also you get that term in real part. Similarly, if you multiply 4 terms of sine and the remaining of cos, that also will come into the real part. So this is how you can find out how many terms will be there in the real part. When two sines are multiplied, that will be NC2 terms, because you are choosing two brackets for sine, so NC2 terms would be there. If you are choosing 4 sines for multiplication, such terms would be NC4. So you can see it will be difficult, or it will be very complicated to write, but I hope you understand how it is done. In fact, what I can do, I can write it definitely, but I will write it in different way. Please understand. I am going to take cos of A1, A2, A3, all the product I am taking as common. Okay, so this will be R is equal to 1 to n. And then now please understand, first term of real part would be 1 only, because when all cos are multiplied, you will get that into the real part. First I am writing only real part. The second real part would be when you are multiplying 2 sine and the remaining cos. If you take all the cos common, okay, so those 2 sine will be now becoming 10, because they will be divided by their respective cos values. So it will become minus of, we can say, summation tan a p tan a q, where p and q are different numbers, or in fact you can write that way also. Okay, similarly, when you are multiplying 4 sines, then iota power 4 will become +1, and the remaining cos, and when you take cos commons, so this will give you 4 tens, 10 AP, 10 AQ, 10 AR and 10 AS, where P will be less than Q, less than R, less than S, less than or equal to N, greater than or equal to 1. So this is how you can write it, although not very practical way, but yeah, that is some decent way I will say. Similarly, you can write it for sine also. This you can write it for sine also. I may skip this part, maybe I can write it directly. Sine of A1 plus A2 and so on. That will be actually the imaginary part. So that will be again product of all the cos. Okay, and then the first imaginary part will be coming when one sine is multiplied with all the cos. So that there will be one sine, all cos. If you take all cos common, so all cos going out, this sine will become 10. So here it will be just summation of 10 A R, you can say. R equal to 1 to n. Then minus sign will come and there will be 3 tens, 10 AP, 10 AQ and 10 AR. Here also P less than Q less than R less than or equal to n, greater than or equal to 1 and so on. Okay, so this is the formula for sine. Now if you are looking for 10, I think it will be just the division of these two things. 10 of, I think I have written n extra here, 10 of A1 plus A2 and so on, AN. Okay, in fact this continued product of cos will get cancelled and we will be getting all these terms of sine. In fact, this is also some formula given in many books at many places. So in my first term, in the numerator, the first term would be, you can write this as S1. S1 means sum of tens taken one at a time. Then minus S3. That means it will be sum of all the tens taken 3 at a time. The product of 3 tens at a time. So 10A, 10 AP, 10 AQ, 10 AR. All possible combination of that will be here S3. Then S5 and so on. Here it will be 1 minus S2 plus S4 and so on. So this is how your 10 A1 plus A2 plus A3 up to AN can be derived. Now let's take one question. Here we are given Z is a non-zero, non-real complex number. Non-real complex number. We have to find the maximum value of imaginary part of Z power 5 upon imaginary power imaginary part of Z power 5 upon fifth power of imaginary part of Z. This is what they are asking. So without loss of any generality, we can take Z as R into cos theta plus iota sin theta. Okay, in that case Z raised to the power 5. In this case Z raised to the power 5 will become R power 5 into cos 5 theta plus iota sin 5 theta. Okay, now what they are asking? They are asking the imaginary part of Z power 5, which is actually R power 5 sin 5 theta upon fifth power of imaginary part of Z, which is R sin theta. So R sin theta whole power 5. So this will become sin 5 theta upon sin raised to the power 5 theta. Okay, now what is sin 5 theta? If you remember, it will be imaginary part of cos theta plus iota sin theta whole power 5. The same method I explained in my very first slide upon sin power 5 theta. Okay, you may not remember the result for sin of 5 theta, but I think this is not difficult. I think you can definitely remember how it is coming. So then you just have to focus on the imaginary part. So the first term of this of the expansion of this with imaginary part would be 5c1, okay, where cos power will be 4 and sin power will be 1. Then there will be minus sign because sin cube, iota cube will be there. So 5c3 and cos square and sin cube theta. Okay, and then next would be sin 5 also. Yeah, then next would be sin 5 also. So let me write here only and that will come with plus sign. So 5c5 and sine raised to the power 5 theta and whole divided by sine power 5 theta. Now if you divide them, you will be getting, I think, cot raised to the power 4 theta. I think I have not written theta here. Cot power 4 theta, that will be multiplied with 5, minus 5c3 is 10, and here also I think I have not written theta, so that will be minus cot square theta and then plus 1. That's it. They have said non-real complex number, that means sine theta cannot be 0. If it is non-real, so sine theta cannot be equal to 0. That is what they are saying. Okay, now this is just simple question of now quadratic, isn't it? You can write this as 5 common. Okay, so cot power 4 minus 2 cot square, so it will be cot square minus 1 whole square, you can write. Okay, and it will be plus 5, you have to subtract 5, so overall it will be minus 4. Okay, so if we are looking for the minimum value, so minimum value will be 4 when cot value becomes equal to 1. So the minimum would be is equal to minus 4, and it will be when cot square theta becomes equal to 1, and that's it. Okay, I think here answer is marked maybe. So answer is C here. Okay, one more question I have got for you, and that says without using individual values of cot 20, cot 40, cot 60, cot 80, evaluate the value of the expression. This cot power 4, cot power 4 20 degree, cot power 4 40 degree, cot power 4 60 degree, cot power 4 80 degree. I think we already know cot 60, so we may not find this, but I will be doing something where we will be getting everything directly. Okay, now how I am going to do, please listen carefully. In this case, because we are given by 9, so I will start with tan 9 theta formula. Please listen carefully how tan 9 theta will help here. Please understand. So I am going to take tan 9 theta is equal to 0. Okay, now if I take tan 9 theta equal to 0, that means the possible values of theta can be pi by 9, 2 pi by 9, okay, and so on. I think it can be up to 8 pi by 9, and rather pi by 9 also. Why not pi by 9? 9 pi by 9, so pi, maybe I could have taken 0 here, and all the remaining values after that, try to understand. Tan being periodic function, so all the values for the remaining angles that will be coming beyond that will be having same values that initial values are having. My plan is to get a polynomial equation in terms of tan theta, and how tan theta polynomial can be created, now you know it, because tan 9 theta, this formula we know directly, isn't it? I think this is something we derived it here, so I will be using it. Okay, and one more thing, because it is equal to 0, so I need not to be bothering about the denominator thing. I will be writing it directly for numerator. So tan 9 theta means it will be 9c1, and that will be tan theta. Only odd powers are coming in the numerator, so 9c3 tan cube theta, okay, plus 9c5, it will be 10 raised to the power 5 theta, then 9c7 10 raised to the power 7 theta, and plus 9c9 10 raised to the power 9 theta. Now you can see it is a 9-degree polynomial, and it will be having 9 roots as 10 pi by 9, 10 2 pi by 9, and so on. Okay, here 10 pi is not needed. In fact, tan pi is coming because of the factor of tan theta. You could have said tan pi, or you could have said tan 0 also. So if I take tan theta factor out, and if I write the remaining thing here, I think I will only be losing that root tan 0, tan pi, which anyways I am not looking for. My idea here will be that I will create a polynomial whose roots are in terms of cot, maybe cot pi by 9, something like that. Let's see how it will come. So if I remove 10, and let me write that things first here, so that will be 10 power 8 theta, okay, and then minus 9c7. 9c7 is how much? 9 into 8 upon 2, I think 24 if I'm not wrong. Let me just check. 9 into 8, how much? 72 upon 2 factorial. Yeah, it has to be 24. Sorry, 9 into 8, 72 by 2 is 36. Sorry, 36. So 10 raised to the power 6 theta. Okay, then it will be 9c5. The 9c5 value is, I think, 126. So this will be 10 4 theta, and then minus 9c3. 9c3 is, I think, 84. So 84 10 square theta, and plus 9 is equal to 0. Now dear all, this is 8-degree polynomial if you look at this from the angle of tan theta, but it can be a biquadratic also. 4 degree, it can be biquadratic. It can be biquadratic in tan square theta, isn't it? If I take tan square theta as t, this will be a biquadratic in tan square. Now, what will be the root? Try to understand. And roots would be, as we have written in the beginning, root should be tan square pi by 9. If I am writing this as a biquadratic in tan square, its roots would be tan square pi by 9. Let me write in, or maybe pi by 9 is fine. I could have written as tan 20 degree also. You may relate more than tan square 2 pi by 9. Okay, then tan square 3 pi by 9. And then tan square 4 pi by 9. Okay, after that it will be tan square 5 pi by 9. But you may agree with me, and that's not very difficult to understand, tan 5 pi by 9 and tan 4 pi by 9 are same. Then tan square 6 pi by 9, I think this is not defined actually, so this will not come as a root because it is just 3 pi by 2, that is not defined. Okay, so leave that thing apart. And then tan square 7 pi by 9, tan square 7 pi by 9 is same as tan square 2 pi by 9, and then tan square 8 pi by 9 is same as tan square pi by 9. So what I am suggesting, if it is a 8-degree polynomial, it is 8-degree polynomial, if you consider that as a polynomial in tan theta, then you will be having 8 roots: tan pi by 9, tan 2 pi by 9, tan 3 pi by 9, and so on. But if you are considering it as a polynomial in tan square theta, this has to have only these 4 roots. The other roots which would have been there if it's a polynomial of degree 8, they will be actually having negative value of these 4, but after doing the squaring they have same values. So the roots of this polynomial of 4 degree will be this only. I hope you understand what I'm saying. Now if these are the roots, I think we are looking for 1 upon alpha square plus 1 upon beta square plus 1 upon gamma square plus 1 upon delta square. If roots are alpha, beta, gamma, delta, cot power 4 will be 1 upon alpha square if this is alpha, and likewise. Now let me know, can we not do this question directly, because it is just a question of sum of roots, product of roots. Okay, so I will not solve this completely. I have given the solution of this question in my session notes. Please go through it. The answer of this comes out to be, I think, 532 by 9. There are other ways also, but most of the methods are having this kind of polynomial formation. You may do it with the help of tan 9 theta or some other way also, maybe tan 3 theta. But in most of the ways where you are not supposed to use the values of tan 20, cot 20, cot 40, it will be done that way only. Now if you do not know how tan 9 theta is coming, I think you will not get this idea of solving this, and I think that is very efficient method of solving this question. Okay, now these formulae. Now second thing, third number is the summation formulae of cos and sine when their angles are in AP. Actually, if you are looking for these series, let me call this as C and let me call this as S. Okay, this can also be done with the help of with the help of this complex number. Let's see how we can do it. So cos plus iota sine. You might have done these things with the help of telescopic sum, where sine d by 2 is multiplied and divide. That is one very good method, but let me see how you can do it with cos plus iota sine, that is complex number method. In this case, if you write cos plus iota sine, I think the first two terms, this and this, when combined, they will give you e power iota a. Then e power iota a plus d, e power iota a plus 2d, and so on. There will be total n terms. There will be total n terms. By the way, the result of these two series is a must. You should remember it, because there have been questions on based on this thing in exam. Okay, so now if we are looking for the sum of these n terms, I think it's a GP, because every time you are multiplying by e power iota d, and first term is e power iota a. So this, its sum would be e power iota a minus e power iota d whole power n upon 1 minus e power iota d. Okay, before I go further, I would like to tell you one important result that can be useful for you, and that I have given in my session notes also, and that result I will be using in later part also. So please understand what I am going to tell you. If you are looking for this e power iota theta, e power iota theta, okay, this will be equal to 2 cos theta by 2 into e power iota theta by 2. You can derive it by writing e power iota theta as cos theta plus iota sin theta, and then doing some trigonometric calculation. Okay, if you're looking for 1 minus e power iota theta, okay, it is same as, although you can derive this also with the help of trigonometric results, but I will like to tell you it is actually the same thing as we have written it here, e power iota pi plus theta, because e power iota pi is minus 1. So now if you open this with the help of this rule, this result, it will be 2 cos theta plus pi by 2 into e power iota theta plus pi by 2. So what will this become? I think cos pi by 2 plus theta is minus sin theta, so that will be minus 2 sin theta by 2. Okay, and here e power iota pi by 2 is iota, e power iota pi by 2 is iota, so you can write it as iota, and then it will be multiplied with e power iota theta by 2. Okay, so this is the result I will like you to use here in this expansion, in this expression actually. So that will become e power iota a. In the numerator, it will be I can write minus 2 iota sine of, that was theta by 2, so it will be n d by 2 into e power iota theta by 2, means it will be n d by 2. In the denominator, it will be minus 2 iota, and then it will be sine of d by 2 into e power iota d by 2. Okay, now you can see this 2 iota will get cancelled, and we are having sine n d by 2 whole divided by sine d by 2, and here if I club all the powers of e, it becomes e power iota a plus n minus 1 by 2 into d. You can check, e power iota a plus n minus 1 into d by 2. Now this is what cos plus iota sine. Now I think we are done. You just need to write real part and complex real part and imaginary part. You will get cos and sine. Cos series, sine series will be obtained directly. In fact, here you can check, this angle is always the average of first and the last one, average of first angle and the last angle. Okay, I will not do it further. It is just writing cos plus iota sine, and then it is done. So this is how you can derive it also. One more thing that I have taken from integration. You might have done this integration with the help of integration by parts. I will tell you the integration of these two with the help of complex number, and which is super easy. Please see how that is super easy. What I will do, I will write this as, let's say, cos. I will write this as a sine. What is this integral? E power ax into cos bx plus e power ax sin bx. This I have multiplied with iota. Now I can bring all these functions inside single integral sign, and then it will become e power ax into e power iota bx dx. This cos plus iota sin b becomes like this. Now this is actually integration of e power x common a plus iota b. So I will be dividing by a plus iota b to get the integration of this. The arbitrary constant we can add individually for this and this separately. So let's focus on only the function part, not the arbitrary constant part. Okay, now after that I think it's simple. Maybe you can rationalize this, or you can say multiplying by a minus iota by in numerator and denominator. That way you can do it, but I will do slightly different. Please see, e power x into a plus iota b. I can write a plus iota b as its mod into e power iota alpha. Alpha is the argument. So if alpha is the argument, that means cos alpha will be equal to a upon root over a square plus b square, and sin alpha will be equal to b upon root over a square plus b square. Okay, I will take this in the denominator directly because that way it will be easier to do. So this becomes equal to 1 upon root over a square plus b square into e power ax we can write separately, and the portion where power where iota is there in the power we can write separately. So e power iota bx minus alpha. Okay, so the integral of this c, that means this first integral will be the real part, that is 1 upon root over a square plus b square into e power ax, and the real part means cos of this thing, which means cos of bx into cos alpha plus sine of bx into sine alpha. Now these values of cos alpha, sine alpha, if you put, you get the integral directly. Okay, now I have taken time only to explain you. If you know it already how it is done, I think it is not very difficult to do it. There is no need of any integration by parts. You do directly the integration just by substitution, you can say, or I think this kind of integrations are done directly, where the function is a linear substitute of x, you can say, where you are just dividing by the coefficient of x. So this is how it is done. Similarly you can do for sine also. Okay, all these proofs I have given in my session notes. Now I am coming to the most important part of this session, that is application of nth roots of unity. Okay, in fact I will talk about nth root of -1 also in one of my question, but let's see how this is used. But before that we should understand what is the nth root of unity. So when we solve for z raised to the power n is equal to 1, okay, so that's an n degree polynomial. Obviously one root is 1, but there are other roots as well. Okay, they are, let's say, alpha 1, alpha 2 and so on. So there are total n roots. One is 1 and others are alpha 1, alpha 2, alpha n minus 1. Now using de Moivre theorem, we can say this 1 is actually e power iota 2 r pi. In general r pi we can write, and this n will come here. So you can see this z will be equal to, if you take r as 0, it will be 1. If you take r is equal to 0, it will be e power iota 2 pi by n. If you take r is equal to 1, which I am calling as alpha 1. Similarly, if you take r as 2, it will be e power iota 4 pi by n, and that is alpha 2 and so on. R is equal to last one would be n minus 1, because if you take r as 1, n, then you get same value as we were getting as r is equal to 0. Okay, so this will be e power iota 2n minus 2 upon n pi. Okay, so these are the values of alpha 1, alpha 2, alpha n minus 1. There are some geometrical application, some geometrical notations also, or you can say representation also of these roots. This is 1, if this is a unit radius circle, so your first root comes here, your second root alpha 1 will come here, which will be making an angle of 2 pi by n with this 1, and then other root will be making 2 pi by n once again, and so on. Okay, so this is how all the roots are distributed there, but I will focus on this part. 1 e power iota 2 pi by n, e power iota 4 pi by a, and so on. Let's see how we are going to make the use of these nth root of unity. So my first result is there in that screen. You can see we have to prove that sine pi by n, sine 2 pi by n, and so on, sine n minus 1 pi by n is equal to n upon 2 raised to the power n minus 1. Okay, for any n natural number. Let's see how this can be done. Dear all, I will not suggest that you remember it, but I will definitely suggest that you should know how it is coming. The product of sine when angles are forming AP, I think we have done for summation but not for product. This will come using this nth root of unity. How? Please see. So as I told you, z raised to the power n minus 1 equal to 0 has roots as 1, alpha 1, alpha 2, and so on. So using factor theorem, I can write this like this: alpha 1 z minus alpha 2, and so on, z minus alpha n minus 1. Okay, here this alpha r in general is e power iota 2r pi by n. Like if you take alpha 1, it will be e power 2 pi by n. If you take alpha 2, it will be e power iota 4 pi by n, and so on. Now what we have to do, if I do some substitution before that, please understand, we can also write this same expression as z power n minus 1 upon z minus 1. And if you divide it, it will give you z power n minus 1 plus z power n minus 2, and so on, plus z plus 1. And this will actually be having the remaining factors, like z minus 1 was divided, so this polynomial of degree n minus 1 will be having the roots like z minus alpha 1, z minus alpha 2, and so on, z minus alpha n minus 1. Now what are we going to do? I am just going to put z is equal to 1 and take mod on both sides. And take mod. Okay, if you put z is equal to 1, so this side will become equal to n, and on the right side it will be mod of 1 minus e power iota 2 pi by n, then 1 minus e power iota 4 pi by n, and so on, 1 minus e power iota 2n minus 2 upon n into pi. Now I think I have already told you this thing, that for 1 minus e power iota theta, the mod has to be 2 sine theta by 2. Mod actually, because sine may be negative, so 2 sine theta by 2 will be the mod of this thing. If you remember that slide, I'm talking about this one. So this is 2 sine theta by 2 into iota into e power iota theta by 2. So the mod of this 1 minus e power iota theta will be just 2 sine theta by 2. That's it. Okay, so if that is so, I think we are done, isn't it? Yeah, I think we are done. Please check. I think this will be 2. Actually 2 will come from all the n minus 1 brackets, so it will be 2 power n minus 1, and then sine of pi by n, sine of 2 pi by n, and so on, sine of n minus 1 upon n into pi. You can remove mod directly because all the angles are in first or second quadrant. N minus 1 upon n is less than 1, multiplied with pi will give you lesser value, so all the sign will be positive. So I think I can directly say mod is not required, and that is what we are looking for. Sine pi by n, sine 2 pi by n, and so on, sine n minus 1 pi by n is equal to n upon 2 power n minus 1. That's it. Can we have this result for cos also? Definitely we can have, but for that cos I will need to adopt slightly different approach. Actually there are two things. First we have to make cases. One will be when n is odd and one will be when n is even. I think this is the case when n is odd. Okay, this is for n odd. I'll show you how. Yeah, odd. For n odd, in the previous this result, let me call this as equation number 1. Okay, so I will be putting z equal to -1 directly in this equation number 1. That's it, -1 I said. So if you put -1, please see and take mod. So what are we going to do for this one? For n is equal to odd, for n odd we will be putting z equal to -1 in equation number 1 and take mod on both sides. Okay, now understand this thing. If n is odd and if you put z is equal to -1, this will be -2 here, this will be -2 here, so that will be 1. You can check from here also. If n is odd, so this will be odd number of terms, because z power 0 we are starting with, total n terms are there, starting with 1, then -1, then 1, then -1. So if you add all of them, your sum will be 1. Okay, so here left side will be 1, whereas on the right hand side we are looking for mod of -1 minus alpha 1, -1 minus alpha 2, and so on. Okay, so this is same as I write 1 plus alpha 1, 1 plus alpha 2, and so on, 1 plus alpha n minus 1. You know alpha 1 means it is e power iota, I think 2 pi by n, yeah, 2 pi by n, and alpha 2 means e power iota 4 pi by n, and so on, 1 plus e power iota 2n minus 2 upon n into pi. Okay, now I have talked about this also already. So the mod of this will be 2 cos pi by n. Okay, and these are total how many brackets? I think once again n minus 1 brackets. So n minus 1 if you write here, and all the cos they will be coming with mod here, pi by n, and it will be 2 pi by n, and so on, cos of I think n minus 1 by n into pi. Okay, but here there is one more thing, because you can see it is not matching with this. There is one more thing here, please understand, and that is that if you look at this first one and the last one, okay, this is pi by n, this is pi minus pi by n. If you simplify it, it is pi minus pi by n, and you know cos theta and cos pi minus theta are negative of each other, but difference is only of minus sign. Magnitude will be same. So what I can do, I can write this 1 which we obtained here, this 1 which we obtained, we can write this as 2 raised to the power n minus 1, and inside the mod sign I can write square of this, because the last term is actually same as cos pi by n, only differences of minus sign, but because of mod that minus sign will go. And similarly cos square 2 pi by n, and so on. Now because n is odd, so these terms are n minus 1 in number, so they are total even number of terms. So if you make the pairs, first with last, second with second last, and so on, so you will be able to complete all the pairs. There will no terms remain, and the last one would be, you can check, it has to be cos square n minus 1 pi upon 2n. Okay, this is equal to 1. Now all the angles here, you can see are in first quadrant. So the value of cos will be positive. So if I take square root both sides after removing mod and taking square root, this square sign will also go, and I think we are done then. We will be getting cos pi by n, cos 2 pi by n, and so on, cos of n minus 1 pi by n, and that will be equal to 1 upon 2 raised to the power n minus 1 whole under root. Okay, so this is how it is done. What we did, we put z is equal to -1. For earlier one we put z is equal to 1, But you can understand if z is even number, sorry, n is even number, then this will be 0. Okay, so and then if you take mod, you will not get anything out of it because it has already become 0. So for even we have to take it separately. This was for n odd, this was for n odd. Okay, for n even the result is slightly different. This is for n even. I'll show you how it is going to come. For n even, try to understand that z power n minus 1. Okay, its factors were z minus 1, z minus e power iota 2 pi by n. Instead of alpha 1, I am writing 2 pi by n. I hope that is fine. Then for alpha 2, I am writing e power iota 4 pi by n. And so on. Now, if we keep on doing like this, and because n is even, if n is even, you can see there will be point in between where you will be getting z minus e power iota pi. Okay, because my last term was, if you remember, it was z minus e power iota 2n minus 2 upon n into pi. So there will be a value in between where this 4, 6 and so on will become n, and that n upon n will become 1, and you will be getting z minus e power iota pi. I hope you are understanding it. This will happen only when n is even. In fact, you can think of that way also, that n is even, let's say z power 4 or z power 6 or z power 8. In this case, you will be having 1 also as a root and minus 1 also as a root. 1 also as a root and minus 1 also as a root, and then other imaginary roots. So in this case, this bracket actually signifies that minus 1 will also be root. So this will become actually z plus 1, z plus 1. So if n is even, you will always get minus 1 also as a root. So this is z plus 1. Okay, and I combine this z plus 1 with z minus 1. If I combine this z minus 1 with z plus 1, I think we can write this is z square minus 1, and I will take this side z power n minus 1 upon z square minus 1. So these two brackets I have taken on the left hand side. If you expand it, okay, z power n, you can write it as z square power n by 2 minus 1. This thing here can be written as z square power n by 2 minus 1 upon z square minus 1. Then I think I can open it the way I did for this thing. I think we can expand this also directly. How? We see it will be z square power n by 2 minus 1 plus z square power n by 2 minus 2. What happened? Yeah, thank God. Okay, and so on. This will go till z square and plus 1. Okay, now this will be equal to the remaining brackets, this bracket, and all the brackets. So let me write the brackets: z minus e power iota 2 pi by n, z minus e power iota 4 pi by n, and so on. Okay, the term just before that would have been, I will write that also, that is z minus e power, this was actually n upon n, so the term before it would have been n minus 2 upon n pi. Okay, this is n upon n, the term before it would have been n minus 2 upon n, and just after that would be z minus e power iota n plus 2 upon n into pi, and so on. And then this last term, that is z minus e power iota 2n minus 2 upon n into pi. Okay, now here also what we have to do, we have to put z equal to minus 1 and take mod both sides. Z equal to minus 1 will give you these brackets, these terms are, I think, n by 2 in number, you can count. So that will be n by 2 here, because every one will become 1, 1, 1. Okay, and on the right hand side, if I start taking the mod, okay, so you can see for minus 1 and then you take mod, it is like 1 plus this thing. So first bracket will become 2 cos pi by n, mod, then 2 cos 2 pi by n, and so on. This one will be 2 cos n minus 2 upon 2n into pi. This one will be 2 cos n plus 2 upon 2n into pi, and so on. Small space, so I have to finish it with this only. I can write this as 2, I can cancel, so that will be n minus 1 upon n into pi. Okay, now as I did earlier also, you can now see this pi by n and this n minus 1 pi by n, they are having same value, only difference of magnitude. So I can combine these two. So cos square pi by n, similarly cos square 2 pi by n, up to cos square n minus 2 pi by 2n. Now you can see this is the same formula which you will get if you take square root both sides. Take square root both sides and you will get this result. Is it okay? Cos pi by n, cos 2 pi by n, and so on, cos n minus 2 pi by n, and its whole square would be n upon 2 power n minus 1. How many terms are these? How many total terms were there? Here you can see these terms were, really sorry for all these confusion, I hope space would have been more. So these are total number of terms are n minus 2, because one z minus 1 and one z plus 1 has been taken that side. So these brackets are actually n minus 2. So from here 2 common will be n minus 2 times. So 2 power n minus 2, and there is 2 on the other side also. So it will give you 2 power n minus 1, and there was n also, and then under root, so you get the answer. Okay, I would have got one step, I would have written one step also, but I hope that is fine. After doing this step, what I am going to do, I am taking 2 common, that is coming n minus 2 times. So 2 power n minus 2 going that side will give you n upon 2 power n minus 1. And all these terms are actually cos square pi by n, cos square 2 pi by n, and so on, cos square n minus 2 upon 2n into pi. So that is how this is coming. Okay, now based on that, there can be many questions like sine 1, sine 2, sine 3. I think this A part is nothing but that result. If you remember this result of sine, if I take n as 180 degree, okay, n as 180, and we write pi in degrees. I think pi by 180 will be 1 degree, then sine 2 degree, sine 3 degree, sine 179 degree, and that will be equal to 180 upon 2 power 179. So you can see this question can be done directly. This sine 1, sine 2, and so on, sine 179 degree will be equal to, as I told you, n upon 2 power n minus 1, 179. Let me just check whether this is correct or not. Yeah, n upon 2 power n minus 1 for sine. In case of sine also, we could have combined first with last because they will be having same value. In fact, in this question, we have to do it. So sine 1 into sine 179 is like sine square 1. Similarly, sine square 2, and so on. It will be sine square 89 degree. And then sine 90 is 1, so we can leave it. In fact, here also you can think of that sine 90 was not there, and that will be equal to 180 upon 200, 2 raised to the power 179. Now we have to take the square root both sides. So sine 1 degree, sine 2 degree, and so on, sine 89 degree. This will be equal to, if you write this as 9 into 10. Okay, so that will be 3 root 10 upon sorry, not 9 into 10, 9 into 10 into 2. So that 2 will make this power 1 less. So this will be 2 power 178, and you take square root, so power will be 2 power 89, and this is done. Okay, I will not say that you remember this formula, but I will definitely say you should know how it is coming from. Okay, similarly for B part, I think this is just of that cos formula where n is taken as 45. Then this will be cos 4 degree, because cos, if you remember it, this pi by n, for n odd actually we have to take, because 45 I am going to choose, so pi upon 45 means 4 degree, then 8 degree, then 12 degree, and so on. If we take n as 45, it will be 1 upon 2 power 44, taking square root will give you 1 upon 2 power 22. So cos 4 degree, cos 8 degree, and so on will be equal to 1 upon 2 power 20. So this is how this is done directly. In fact, there is one more question I have taken. I think you will feel this is direct. Sin pi by 7, 2 pi by 7, 3 pi by 7. Just take n is equal to 7 there. N is equal to 7 there, and then take square root. You will get this directly. Okay, now another question. A1, A2, A3 are the vertices of n-sided regular polygon inscribed in a circle of a radius unity. Then prove that mod of A1 AR plus 1, then product is equal to n. I think this is also directly based on nth root of unity. How? Please see. If I am having regular polygon of n side, we can think of that it is created with the help of all the nth root of unities. Okay, so this is, let's say, 1, then other vertex of your polygon is alpha 1, then alpha 2, and so on. Okay, so you can see that this is, let's say, A1, this is, let's say, A2, this is, let's say, A3, this is, let's say, A4. Why a regular polygon? Because all the roots on this unit radius circle are forming same angle. If you choose two consecutive roots, they are forming same angle. So this has to be, these angle has to be same, and that is possible only if this is a regular polygon, means all the sides A1, A2, A2, A3, A3, A4, they all are same. Okay, now they have said vertices of a n-sided regular polygon inscribed in a circle of a radius unity. This question is actually of this nth root of unity only. Now they are asking of mod A1, A2. Isn't it 1 minus alpha 1? Is it not 1 minus alpha 1, the mod of A1, A2? Then A1, A3, that will be 1 minus alpha 2, then 1 minus alpha 3, and so on, 1 minus alpha n minus 1. If you look at all the vertices, this is A1, A2, A3, the last one would be AN, yeah. When R is equal to n minus 1 we are putting, the last one will be AN here. So we are looking for product of all these distances. Now, this is nothing but, if you use that factor theorem, it is actually z power n plus z power n minus 1 and so on plus z plus 1 when z is equal to 1. I hope you remember it. See, these are the factors of this. One mistake. Yeah, one mistake. Yeah. These 1 z minus alpha 1, z minus alpha 2, z minus alpha 3, z minus alpha n minus 1 are the factors of this expression only. Okay, and then if it is 1 minus alpha 1, 1 minus alpha 2, we can think of, we have put z is equal to 1. So if z is equal to 1, so we get z is equal to 1 here also, and this is actually equal to n, and I think we are done. Okay, you can remember, I will not say remember, but you can keep it in your mind that in regular polygon there was some property like product of distance of one vertex with all other vertices is always equal to n. Like if it is a triangle, it will be 3, if it is a square, then it will be 4, like that. But circle should be of unit radius, yeah, based on that. Okay, a few more things. In fact, I think 2 or 3 things I am more having for this session. So we have to prove sine n theta formula in terms of sine theta plus pi by n, sine theta plus n minus 2 pi by n, and so on. You might not have seen this thing before, but let me tell you, this can also be done with the help of complex number. Very easy. I'll show you how it is done. Similarly for cos n theta also. This is not a standard result. Okay, so don't take any don't worry about it that you do not know it already. This is just like a question, but I found use of this thing in one of my question, and in that question I realized that sine n theta should have some result like this, and which I was able to derive with the help of nth root of unity. I will show you how. Okay, so let's focus on first one. So I will be starting with that z power n minus 1 equal to z minus 1 z minus e power iota 2 pi by n and so on only. Same nth root of unity. Very simple concept. Z minus e power iota 2n minus 2 upon n pi. Now what is to be done? You have to put z equal to e power iota 2 theta and take mod on both sides. Z equal to e power iota 2 theta. If you put it here, you will be getting e power iota 2 theta minus 1, and this will be mod of e power iota theta minus 1. This will be e power iota theta minus e power iota 2 pi by n and so on. Okay, I think I have told you already how this mod is written. Okay, this e power iota 2 theta minus 1 will be 2 sine theta. Sorry, 2 sine n theta actually. 2 sine n theta. I have told you already. Okay, if you are having any confusion, just write this as cos plus iota sine. You will get 2 sine n theta as the mod. In fact, you can put mod sine also here. Equal to, this will be 2 sine. I think I have made one mistake here, not theta, it was 2 theta. Not theta, it was 2 theta. 2 theta. So this will become 2 sine theta. This will become sine theta minus pi by n with 2 also here. The mod of this would be 2 sine theta minus pi by n. Okay, you can derive with the help of the result of this also. Let me show you how. If you write this after taking e power iota 2 pi by n common, yeah, visible. If you take this thing common, your expression will be e power iota 2 theta minus 2 pi by n minus 1 ka mod. The mod of this will be 1 only. Okay, and the mod of this, as I have told you, will be 2 sine the half angle of this, that is theta minus pi by n ka mod. Why I am keeping mod on sine every time? Because sine may be negative also, so that is how it is coming. So this is 2 sine theta, this is 2 sine theta minus pi by n, and the next one will be 2 sine theta minus 2 pi by n and so on. The last one would be 2 sine theta minus n minus 1 upon n pi. Okay, so this is what we are getting, but my result was supposed to be with plus sign in between. Okay, so if it is with plus sign in between, so think of this thing, that this term here, if I add pi to it, and you know sine pi plus theta is equal to minus sine theta, but as far as mod is concerned, I think this is same. If you add pi to this angle, the sine of pi plus theta ka mod and sine theta mod, they will be same. So if I add pi to it, if you add pi to it, please look at this carefully. If you add pi to it, I think this will become 2 sine theta plus pi by n. You can check. Pi, if I am adding, so this 1 into pi will get cancelled, so theta plus pi by n will remain. Similarly, if I keep adding pi to all of them, it will be 2 sine theta plus n minus 2 pi by n, and here sine, actually 2 also, 2 sine theta plus n minus 1 upon n into pi, and this I will leave as sine theta only, and into 2 here also, Okay, so this is what we are getting. Now you can think of this is this only, this is this, this is this, and this is this. How many terms of sine? I think I am having all n brackets with me, so this will be 2 power n here. Okay, so 2 power n means it will be 2 power n into the product of all this sine theta, sine of, I will write that term first, so theta plus pi by n, then sine of theta plus 2 pi by n, and so on. Sine of theta plus n minus 1 by n into pi. I think everything is visible. Yeah, is visible. Theta plus n minus 1 pi by. Okay, here there is one thing, there is one problem. You may say that it was a mod. So how can we say that sine n theta will be equal to this thing without mod also? Okay, let me write it on the next slide. Okay, so what we got sine n theta equal to, this 2 will cancel 1 power, so it will become 2 power n minus 1 into sine of theta, sine of theta plus pi by n, sine of theta plus, what was that, 2 pi by n. Yeah, sorry, just got confused. Two pi by n, sine of theta plus 3 pi by n, and so on. Let me write the last term also, theta plus n minus 1 pi by n also. Now it should have been with plus or minus sign. Now please think of this thing, that it has to be some identity which will be valid for all theta. Okay, now I can figure out whether there will be plus sign or minus sign for some angle theta. I can claim it will be having same angle for all thetas. Okay, now I am going to take theta as, please understand that, pi by n minus h. I will be taking an angle that is slightly lesser than pi by n. Okay, now if theta is like this, you can see all these angle, because it is less than pi by n, slightly less than pi by n, so that angle will be in first quadrant. This will be 2 pi by n minus h, so again less than pi. In fact, here also if you can see pi by n, if you add, okay, pi by, yeah, if you add pi by n minus h, if you write pi by n minus h in place of theta, it will be pi minus h, you can see it. Okay, so that means this will also be in second quadrant. So all these sign are positive, whereas here also you can see n theta will be pi minus nh, that will also be in second quadrant, so this will also be positive. So you can see for this particular angle theta, both sides are positive, so it has to be plus sign only, that's it. Okay, I hope that is clear. Now there was one more thing for cos. Yeah, there was one more thing for cos. This can also be done the same method. You just have to put z equal to minus of 1 minute, sorry. Yeah, for cos n theta it is not that direct, sorry. I think I need to tell you that also. Okay, I'll come to that. Before that, let me take this question first. Now here you can see the question says sum of cosecant square k from 0 to 6 upon 7 cosecant square 7 theta. Now this question is directly based on this result. Please understand. How can we directly based on that result? Please see, cosecant square theta, if you remember, is the differentiation of minus cot. Okay, let me start that way. Cosecant square x is the differentiation of minus cot. Okay, and minus cot is the differentiation of log sine, or maybe minus sign, you can put it here. Okay, so what you have to do for this question, you just have to take the log and then differentiate 2 times. Okay, if you if you take the log, let me do it. So it will be log sine n theta is equal to log of 2 power n minus 1 plus, let me write it in the form of summation, log sine of theta plus r pi by n, where r is starting with 0 going till n minus 1. Now differentiate once, not once, twice actually. For sine n theta, differentiation will be, log sine n theta will be n outside cot n theta upon sine in the numerator cot, so cos of cot. Okay, then one more differentiation will give you minus n into cosecant square n theta. This n will also be square here. So what we are getting, the differentiation of this will be 0, 0. The differentiation of here, this would be just minus sign will be outside, I think. So cosecant square theta minus cosecant square theta plus pi by n and so on. Okay, so now you can see this question, cosecant square pi plus k pi by 7, where k is varying from 0 to 6, is ditto same thing. Here it will become 7 square, that means it will be 49 upon 49 times cosecant square 7 theta. 49 times cosecant square 7 theta. So cosecant square 7 theta will get cancelled. So answer for this will be 7 directly. There is no need to put theta is equal to pi by 8. I think it is direct. Okay. It is just one example that how questions are created. You can get questions from anywhere. Now this question will become very easy if you know how this result is coming. You may not remember it, but if you know how it is coming, the idea for this question could have been, think of some cosecant square where cosecant square is coming. So it is the differentiation of cot. Maybe if you know the sum of all cot, then also this could have been done. But if you know it, then definitely you can do it. Then for cot, it's the differentiation of log sin x. Now if you think of whether sine is having some result like this which can give you sum of cot, so you may find this result useful in such questions. Dear all, I am not discussing the usual questions here. I am always discussing those questions which are all higher on difficulty, you can say. So this is why these sessions are actually very specific to subtopics. Okay, so this is how this was done, and I have shown you how it is used. Now coming to this cos. Okay, let me use the space. Will this white screen be fine? Oh. Let me see if I can use white screen. No. No. Okay. Okay, I will keep. Is there any blank slide here? Yeah, I am having the first one. I will use it. Okay, so I was talking about cos n theta, how it can come. So for that we will require, I will require z raised to the power n plus 1. Actually that is the nth root of minus 1. This is the nth root of minus 1, not 1. Okay, now if you are looking for nth root of minus 1, we will be writing minus 1 as e power iota 2n plus 1, or I will say 2r, not n because n is already there. So 2r plus 1 into pi, that is the general value of minus 1. So using de Moivre theorem or dividing by n in the power, you will be getting this as, first factor will be e power iota pi by n, then z minus e power iota 3 pi by n, then z minus e power iota 5 pi by n, and so on. Z minus e power iota, the last one would be 2n minus 1 upon n into pi, because after that if you do, you will be getting same roots. If you write this r as, see here you have to have n roots only, so here we are getting 1 minute. Yeah, pi by n, 3 pi by n, 5 pi by n, and 2n minus 1 upon n is n roots only. Okay, now if this becomes 2n plus 1, yeah, so it will be same as e power iota pi by n. So these are the distinct roots that will be corresponding to this z power n plus 1 equal to 0. So using factor theorem we have written like this. Now if you remember in that sine n theta, I use z power n minus 1. Here I have used z power n plus 1, and then it will be same. We will be putting z equal to e power iota 2 theta, and then take mod. Now if you take mod, this will become, I can write it directly, 2 cos n theta, and on the right hand side, if you take e power iota 2 theta minus this thing, it will be 2 sine theta minus pi upon 2n mod, and then 2 sine theta minus 3 pi by 2n and so on. 2 sine theta minus 2n minus 1 upon 2n pi. That's it. Okay, I think we are almost done. The only thing remains is that how to get rid of this mod. But before that, one more thing, because I think what formula I have given there, that is not minus, it is plus sign, and this minus to plus, that can be done with the same idea which I told you in sine also. Let me first check whether it's a plus or minus. Yeah, it's plus. So what I will do, I will be doing the same thing. I will add pi here. If I add pi here, it will become 2 sine theta plus pi by 2n. If I add pi to this angle, because it is inside the mod, so minus sign has no impact, it will be pi upon 2n. Similarly, if you add pi here, it will be 2 sine theta plus, I think it will be pi, it will be 2n minus 3 upon 2n into pi. This will be 2 sine theta plus 2n minus 1 upon 2n into theta. एक मिनट, कुछ गलत कर दिया क्या? No, I think it is fine. I'm confused. Yeah, just pi only. Let me just check once again. I have added pi, that's it. So pi upon, this was pi upon 2n actually. This was pi upon 2n, yeah. So upon 2n, yeah, that's fine. Now everything is now sorted. You have to start from that end. So sine theta plus pi by 2n, sine theta plus 3 pi by 2n, and so on. You have to come to this end, and that will be equal to cos of n theta. The logic of using only plus sign is same as I told you in sine. You can choose some angle. Now think of it yourself. I have given that angle in my session notes. If you want, you can go through there also. But this sine, all these signs when multiplied will give you cos n. And here these 2 will be taken n times. There 2 is just once. So this cos n theta will be 2 power n minus 1 into all this thing. Let me see if it is same or not. Let me come to that slide, the last one. Yeah, this one. So cos n theta is 2 power n minus 1, sine of theta plus pi by 2n, sine of theta plus 3 pi by 2n, and so on, sine of theta plus 2n minus 1 pi by 2n. Okay, so this is all about this session. There was few confusions, but I think I managed them well, so you will understand it. If you do not understand, just let me know. Okay, although I have given the session notes very clearly written, very all the expressions are given in that session notes. So wherever you are having any difficulty to understand, please go through it. And still, if you are having any difficulty, just let me know which minute or at which slide you are having problem. Let me know. I will give you some solution maybe. Okay, so that is all for today. I am getting comments in the chat that I should be starting this particular topic or that particular topic. I may be doing that, like coordinate geometry or calculus. these are the two topics which I think you have demanded, so maybe I will take them, but my way of taking them in the sessions would be, it will not be starting from zero, it will be like the basics, okay, and then I will be taking some high level things, or I will be taking the important stuff that you should know, and that may not be that usual, other may not be knowing it, and but they will be useful. Only useful thing I'll talk about, which will give you a confidence while solving questions of JEE Advanced. Okay, so I'm thinking of that thing, but I'm still having many ideas to share with you through these sessions. So maybe 4 or 5 more ideas I'm having or at the moment, and I will be keep working on them, and I'll bring them to you. So that's it. Thank you so much. Bye bacho, take care.